Need to pick up here and talk about a tangent plane. And of course, very much analogous to two-dimensional tangent lines. You know, if we've got this function y equals f of x, and we come out at any particular x value and get our tangent line t at a particular point, then one thing we stressed back when we were doing that, one of the things we stressed was that the tangent line and the function curve, if we're talking about around that particular point, if we zoom in or if we just look at it at that particular point, then let's say, so we zoom in here. What happens between the curve and the tangent line? Well, if we zoom in here, you know, we've got this kind of curve, but you know, as we zoom closer and closer in, you know, the curve is, yeah, kind of straightens out, and the two become pretty much indistinguishable. So if you zoom in far enough, you can't really tell much of a difference at that particular tangent point. So the same is going to be true in 3 dimensions here. Let me try to draw an example here. You know, it gets harder to draw by hand these things, or it does for me anyway. We've got x, y, z. And let's say we've got a nice little, I don't know, paraboloid or something that we want to look at. Okay. All right. And so we want to come out here and at, I don't know, x0, y0. So it's this, drop this point down so the y0 will be somewhere like here. And then, of course, z0 is here. And so, yeah, we get a tangent plane at that particular point. So we want to come up, first of all, come up with the plane, what it is. So let's just say it's kind of flat. I don't know. So there's some tangent plane. It's probably more angled, you know, angled there, but you get the hopefully idea. Okay. All right. So for this particular function here, z equals f of y, we've got this tangent plane at the point P, x0, y0, z0. And again, harder to show, but if we zoomed in closer and closer to that tangent plane, the two would become indistinguishable, the plane and the surface. You know, you have to zoom in a little bit there, but those two would become indistinguishable. So you get a kind of a flat surface for your curved surface. But yet, you know, if you zoom in nearer and nearer to that point. All right. So let's talk about what the tangent plane looks like, which we haven't exactly done yet. But all right. So any plane we know through any particular point, you need. Usually we do a normal vector and the point, but let's just say we've got the point x0 okay. So usually we set it up. You got something times the x minus x0. We don't know what that is right now. Plus then the b times the y minus y0 plus c z minus z0 equals 0. Okay? So that's normally what it looks like. And then, if we have that perpendicular vector, normal vector we called it, we plug that in. However, that's not how we're going to do this one. Okay? In this case, what we're going to do is we're going to get the z minus z0 isolated. Okay? So, all right, so let's see. We would subtract these two and then divide by c, so we get something like this. Z minus z0 equals, it'd be minus a, x minus x0 minus b times y minus y0. And then we divide by the c, and so I just kind of do it like that. Okay? All right, now we're going to kind of forego that. Let's just say that's little a and that's little b, and so we get z minus z0 equals a times x minus x0 plus b times y minus y0, because like I said, we're not going to be using the normal vector here, the a, b, and c, like we normally do here, and so we're just kind of calling whatever that is little a and b. Okay, now what we did do back in the previous section was we talked about partial derivatives, and what we found out was that if we take our partial derivative and so forth, what that does, remember the partial derivative with respect to x gives me a what here at the point? Gives me a tangent line, in essence the slope of the tangent line. So partial derivative with respect to x gives me the tangent line at where? For constant y0. Okay, so it's basically you're intersecting with the plane y equals y0. So let's intersect this with our plane y equals y0. What does that give me? Well, if y equals y0, then y0, that's 0, isn't it? And so we get this, we get z minus z0 equals a times x minus x0, which is just a line. Like we said, it's a tangent line at a point. Okay, so this is a tangent, the tangent line for this surface, if you will, at that particular point. And like we just said, this right here represents the slope of the line. So hence the slope of the tangent line, which, like we said in the previous work, we saw that the slope of that line is going to be the partial derivative. So a is our partial derivative. Since it's the slope, a is going to be the partial derivative with respect to x at x0, y0, right? So this a right here is the partial derivative. Hopefully then, it's not too far of a jump then to say, similarly, what does b equal? What does this b equal? Partial derivative with respect to y of f at x0, y0. Yeah, because in that case we would get, intersect it with the x equals x0 plane like this right here, and so that's going to give me the tangent line at that x0, and so we'd get rid of this, so we'd have z, so that just gives me the tangent line, and b would be the slope of that, which is the partial derivative of y. Okay, so Anyway, what that amounts to then is that the tangent plane then, if we make those substitutions, a and b are partial derivatives like we said, the tangent plane at P, the point P, x0, y0, z0 is then given by z minus z0 equals the partial derivative of x, of f with respect to x at x0, y0 times x minus x0 plus the partial derivative of y at x0, y0 times y minus y0. So that's going to give us a tangent plane at any particular point for a surface, as long as these partial derivatives exist and are continuous near that particular value. All right. Now, what you might note there is the similarity between this, what we have here, and then the point-slope form of a line. What is point-slope form of a line? Y minus y0 equals m times x minus x0. And if we're talking about tangent lines, the slope is the derivative, right? And so that's very, very analogous, yes. Yeah, if we're talking tangent lines, then this right here is the derivative at x0. And so, yeah, we've just kind of leaped to 3 dimensions. So it's z minus z0 instead of y minus y0. And then you got 2 partial derivatives instead of 1 derivative. So very much the same. Very much the same. Okay. So let's do one here. Okay, so let's find the tangent plane to z equals 2x squared plus y squared at the point 1, 1, 3. Okay? All right, so we know, know for our tangent plane, we've got z minus z0 equals f, partial derivative of f with respect to x of x0, y0, x minus x0, partial derivative of y, x0, y0, times y minus y0. All right, so to do that, we need these two things right here, the partial with respect to x, and we need the partial with respect to y. Of, and of course this is z equals, so we do have a function f of xy, right? Okay, so what is the partial with respect to x? Just in general terms, xy, well, very easy. Your y is a constant, and so what would the partial with respect to x of this be? This would be 4x. The y is constant, so it's just 0, okay. All right, then the partial with respect to y of xy would be, well, the x is constant there, and so the partial would be 2y. We want, however, at x0, y0, well, that's these points, right? This is x0, this is y0, and it even gives us z0 to plug in. And so we're wanting f, partial of f with respect to x of x0, y0, which would be 1, 1 here. Well, we just have to know the x, that's 4. 4 times 1. And therefore, the partial of y at 1, 1 would be 2 times 1, so that'd be 2. Pretty much got it, don't we then? So the plane would be z minus z0. Like I said, it was nice and gave us that too. Z0 is 3. We've already computed partial with x at x0 is 4 times x minus x0, that's our 1. This turned out to be 2, and then the y minus y0, so that'd be 2 minus 1. I mean, 2 times y minus 1. Okay? All right, so what we have then, if we, I'm going to go ahead and put it kind of in a standard, standard type form. Z would equal what? 4x minus 4 plus 2y minus 2. Let's go ahead and add the 3 over, so that would be z equals 4x plus 2y minus 3? Minus 3. All right, so that's our tangent plane at 1, 1, 3. All right, now, I did this one because the book also did this one. And so I have some nice graphics you can see there in the book, or let me flip over here for my recording. Okay. All right, so you see there, you got your tangent plane. Get the pen out so I can, in the first one there, right? All right, so the first one shows the, yeah, it's right there on the left. That's your tangent plane, and the curve, and they oriented it. What we got the x-axis kind of coming to, or no, the y-axis coming to us, and the x-axis kind of meeting there in the middle. Z-axis is up. So we've got the tangent. I mean the curve, elliptic paraboloid. They're calling it. And then they've also graphed this tangent plane at 1, 1, 3. So you can kind of see, yeah, it's kind of just skimming the surface there. And so in the middle one, what'd they do? We've kind of zoomed in a little bit, right? Now we're going, instead of y negative 4 to 4, x 4 to negative 4, we're going to negative 2 to 2. And so we kind of zoomed in a little bit to the point there, and you can see, yeah, it's kind of flattening out a little bit, the surface. And then the one on the right, well, they've really zoomed in. Well, we've got 0 to 2 in x and y, and so, yeah, you can really see that the surface now has flattened out because we're not looking at such a big chunk of it, and it's pretty well matching. The tangent plane is still there, okay, in all three. So, yeah, got a pretty good match, doesn't it? So it's the same idea as the tangent line to the two-dimensional curve. Here we're doing 3 dimensions, so we're doing a plane, but the plane and the surface near, so you know, we're looking here 0 to 2, and there's just a little bit of a gap. I mean, the z is, if you get on the edges there, the z values are a little bit, you can see a little gap in there, but not a whole lot, not like you could on the first one on the left. So, all right, so it's